We will now consider first the unimolecular reaction, and the model we'll consider for unimolecular reaction was first provided by Lindemann, and that's why it is called a Lindemann mechanism for unimolecular reaction. So Lindemann mechanism, sometimes it is also called Lindemann-Christiansen mechanism for unimolecular reaction. So unimolecular elementary reaction. So as we said that a molecule is just decomposing into products, but it has to be some energized molecule, because meaning actually what Lindemann said, there should be some collision. If it is a collisionally activated unimolecular reaction, then a bimolecular collision should precede the unimolecular reaction. And then you can always write that to give you an example of the unimolecular reaction. For example, this isomerization, isocyanide to cyanide, and you see some observed rate law, and the observed rate law, which is nothing but if you just write it in terms of the reactant, so I'm using a negative sign, so that is found to be minus K into, or we can just write it as plus here minus here, doesn't matter, CH3NC at high pressure, and at low pressure it just behaves as a bimolecular reaction. It's at low pressure. So usually we write this term, which is minus K into CH3NC, as K observed, in the sense that we take that rate and plot it versus the concentration or the pressure of the gas, but we do not plot the actual rate constant. We actually plot the observed rate constant, which is defined as minus K into CH3NC. We can actually write the minus sign in the other hand and just define the K observed like this, which means at high pressure this will be nothing but equal to K observed, and at low pressure this thing will be nothing but equal to K observed times the pressure of the gas, which is CH3NC. Now in order to understand the mechanism of Lindemann proposed that, okay, fine, you have a similar thing which we have discussed already. Gas first, say the reactant is A, and it first collides with a second gas molecule, which can be the container also, which can be any other gas molecule also, to get basically generate an energized molecule. So A star is nothing but an energized molecule. So it has much more energy so that it can decompose into the products plus the M. Of course, the way we are writing M here, this is slightly different in the sense that this M has now a lower energy, but we are not writing it explicitly. And there's a first equilibrium for step 1, and in the step 2, then this energized molecule gives you the product with some rate constant. Now we have already told you that suppose I'm just writing it as B, and we already told you that what is the rate equation for this kind of reactions, and we can actually use the steady state approximation for S star, and you can easily solve it. I'm not solving it 1 second because we have already shown you how to solve it. So you just have to take the d S star dt that to equate it to 0, and then you can easily figure out what is the rate of the reaction. The rate of the reaction here is dB dt, that you can find as K1 K2 into M divided by K2 plus K minus 1 into M into A. And as before, you can see here this we can actually now talk about the high pressure and the low pressure limit. Now in the high pressure, in the low pressure limit, what happens here is that you have a linear relationship, in the sense now this term, if it is linear, then obviously this term should be much less than this term, which means K minus 1 into, or you see basically observed rate law is proportional to the concentration of the gas. And remember that the K observed was K times M. Now you can say that if it is a very high pressure situation, then the collisional deactivation will be much more. Now what is the collisional deactivation step? This is basically the K minus 1 step. So we have, for the ester, there are two pathways. One is the collisional deactivation, where this is the rate for the collisional deactivation, K minus 1 into ester, and versus you have a reactive pathway for ester, which is K2 into ester. Sorry, the collisional deactivation will also involve an M, because M is sitting here. So now the question is, which rate is faster? Now you can say at very high pressure, when the pressure is fairly high, the collisional deactivation is much more. So this term will be more than this term. So you can easily see that the rate will be nothing but K1 K2 divided by, now deactivation is more, which is this K minus 1 into S star into M, which means you can actually eliminate, when you compare these two terms, you can actually eliminate the A term, A star term, that we exactly did for the steady state approximation. And in that case, this term will now dominate. And then what you have is nothing but K1 K2 divided by K2, which is nothing but K1 K2 into M divided by K minus 1 into M into A, and which is nothing but, now you can see that this M cancels, so you have a combination of rate constant times A, but we said that that we call as K observed. So this is nothing but K observed. So at high pressure it is constant. It's not exactly a constant. It is, remember that the K observed, we are saying that it includes the A inside. And that's how Lindemann actually treated this thing. And at the very low pressure, what will happen, the collisional deactivation term, which is this term, will be much smaller than the K2 term. So we'll have K1 K2 divided by K2 into M into A, and that you can easily write that I'll have something like some rate constant, which is K observed into M. So if I plot the rate of the reaction as a function of this M, we'll see at low pressure region it is linearly proportional to this M, so it will just rise like this. But at a high pressure, you will see that it will be kind of constant, where this rate, or the rate constant, is written in terms of observed rate law, where the concentration of A, or the reactant, is already included or absorbed in the K observed. But of course, the value of the K observed will be different. But from this slope, actually, you can easily calculate what is this composite rate constant. So that way, you can actually describe the variation of the unimolecular rate versus pressure. Now, pressure of what? It is pressure of, in general, any. It can be a pressure of anything, or you can actually insert an inert gas and also then call it as M, and then vary the pressure of the inert gas itself to study the unimolecular reaction. You can consider it as a second body present there, which is not reactive. It is just increasing the pressure, which means actually it is increasing the collision, and thereby it is controlling the amount which is by which the A star is formed, and the amount by which the A star, or the rate by which the A star is also deactivated. So it is controlling this activation and deactivation procedure of the A star without directly taking part in the reaction, because in the reactive path all the A star forms the product, which is the part 2 here. So that's how unimolecular reactions, the kinetics of the unimolecular reactions was explained by Lindemann. Now later on, it was unimolecular reaction has a very, very important role in chemistry. It is extremely important to describe many interesting situations. For example, if I have an energized molecule, how the energy flows within various vibrational degrees of freedom inside the molecule, and that's a fairly complicated problem to address. And later on, after Lindemann, this was a kinetic model, but then people working on reaction dynamics took up this challenge, and there are many interesting models that were developed. First advancement was done by American physicist Cyril Hinzelwood, and then subsequently there a model came where a lot of people contributed. The model is known as RRKM model, and but that we will not discuss in here during this discussion on the reaction dynamics. We will not consider any unimolecular reaction dynamics because that is out of scope, and that needs a lot of understanding of classical statistical mechanics, particularly the understanding of the partition functions and many other things. So we'll skip that, but this is just to let you know that this RRKM model is one of the most celebrated theoretical models which chemists often used, and there's a very beautiful mathematical development as well as a physical insight behind this model, how actually unimolecular reactions take place, how the dynamics takes place. But however, whatever is that model, all this Hinzelwood statement or the RRKM extension to it. Actually, before RRK, the RRKM, there was this RRK model, and then there was a further refinement done by M, which is by Rudy Marcus, and who gave the very interesting picture of these unimolecular reactions. And those are just historical anecdotes, but this work is very famous. And then but the fundamental thing is that this kinetic model which Lindemann proposed is correct, which means that actually any unimolecular reaction, for any unimolecular reactions to happen, there should be a bimolecular reaction beforehand with some third body, or sorry, it's a second body, which is M here, and that collision with the molecule with M produces an energized molecule ester, but the collision activation and deactivation is controlled by the pressure of the M, and that is for sure, that is always that's always held. But the question right now is how the ester is forming the product, the second step. Now all these models which all the dynamical models which I just said, the Hinzelwood treatment or RRK and RRKM, actually focuses on this part. Once we have an energized molecule, how it will take part in the dissociation of the forming the products. The reason is, think about it, if you energize a molecule, then there are, suppose you are energizing a big large molecule where there are many bonds. Now the question is how the bonds will break. Which bond will break? Can you predict it theoretically? And the RRChem theory says that, okay, fine, once you dump some energy into the molecules, first what will happen, all the energy will be statistically redistributed equally to all the bonds, and then the weakest bond has the largest probability of breaking. And that's not very correct assumption, but that's the essence of the RRChem theory. And then people start discussing what is the dynamics, how to basically formulate, write the rate constant, get an expression for the rate constant for this unimolecular reaction. So we'll conclude our discussion on unimolecular reaction here, and then we'll proceed to catalysis. But before that, I'll give you a very brief introduction to the energy of activation. Now, the Swedish chemist Svante Arrhenius did a series of experiments to find this very interesting question: what is the temperature dependence of the rate constant? Temperature dependence of rate constant. Now, rate constant, so far as we have described, doesn't seem to have any temperature dependence because we just took it as a constant. But experimentally, what Arrhenius found is that the K, or the rate constant, has a very strong temperature dependence, and that he found an exponential law, and he found that it can be written as something like this, where there's a factor before the exponential which he called as the pre-exponential factor, because it appears before the exponent, so you call it as a pre-exponential factor. And then there is some kind of energy that he called as energy of activation, which sometimes we call as activation energy, but it is not perfectly correct to call it as activation energy, because activation energy is something different. It has a statistical interpretation, but we'll just call it as an activation energy. Now, this activation energy, or energy of activation, if we draw it in a potential energy diagram, where basically we're talking about how the reaction Gibbs free energy is changing from going from, say, reactant to products. So suppose I have some reactant here, and it is giving me some product. The product energy can be higher than the reactant, it can be lower than the reactant, but that we are not considering right now. It can be higher, it can be lower. Let's say it is lower for the time being. So we are considering a reaction where this reactant is going into product, and we are just asking what are the energetics of it. Now, what thermodynamics told you is that whether this forward reaction is feasible or the reverse reaction is feasible. If the delta G of the reactive Gibbs free energy is negative, then the reaction will be spontaneous, or the forward reaction will be spontaneous. That's what thermodynamics told. But thermodynamics did not tell how this reaction happens, or at what rate the reaction happens. We could actually have a situation that, okay, fine, it is lying at a higher energy. Let me just draw it slightly above. Say the reactant is sitting here, and we have some difference in energy, which is connected to the delta GR. So this is basically the Gibbs free energy, and this is the reaction free energy. So since it is negative, so this reaction will be spontaneous. But the question is at what rate it will go, or how the reaction will change. Is it something like that the reactant will eventually lose its energy and go to product? Now, Arrhenius said no, actually it doesn't go like that. It actually goes through a barrier, which means there is a barrier that every reactant should cross before it forms product, and this barrier is coming here. So EA is nothing but equivalent to this height of this barrier for the forward reaction. Similarly, if you think about the reverse reaction in this case will have a much larger barrier. So it's all about the barriers to the reaction that actually controls the reaction. Now, we'll give you an example or something very interesting that we discussed earlier, but we did not say it very clearly, this thermodynamically and kinetically controlled product. But look at it here. So if this barrier is very high enough, it is coming as exponential minus. So the reaction rate or the rate constant for this reaction will be very low. And if the reaction is actually, if for a particular reaction, if this barrier is smaller, then the reaction rate will be faster. Now consider there is a fixed reaction, which means there is a fixed activation energy. So what we can do is that we can increase the temperature, which means the average energy of the reactant will now increase. It will be here or it will be here, so that it can easily now cross the barrier. So that is the entire concept. So I have an energy of the reactant at room temperature, and there is activation barrier. So I have to cross this energy hill, or sometimes that is called as it's just like crossing a mountain. And you cannot just, it's just a mountain is there, and you cannot go from reactant to the product by creating a tunnel through it. So you have to cross the mountain to go to the other side. And that is the entire idea here. Of course, when I say that this is not possible, this is actually possible. This is known as quantum mechanical tunneling, but we're not going to consider that right now. So going from reactant to product, you have to cross this mountain, and then if you are energetically high, then you have to just spend a little bit energy to cross the mountain. If you are energetically low, so then you have to apply a lot of energy to cross the mountain. So the thermal activation is nothing but basically pushing the reactant to the average number of molecules to a higher energy state so that they can easily cross the barrier. The other way of looking at it is that, okay, fine, I'm not changing the temperature, so all the molecules are sitting here, but can I actually modify the height of the barrier? Meaning, can I actually reduce the height of the barrier? So that is done by catalysis. So catalysis is nothing but it reduces the height of the barrier by providing some alternate pathway. So the reaction doesn't follow now this path, which is known as the uncatalyzed path, but it now follows this path, which is much less energetically, and so energetically much more favorable. That is known as catalyzed path. So we're going to discuss that, how the catalyzed path helps to proceed the reaction. Now you can easily imagine if EA is smaller, the reaction rate becomes faster at the same temperature. So it discussed two different things. One is the temperature dependence of the rate constant, which Arrhenius phenomenologically found, and he gave an equation which is known as Arrhenius equation, and that depends on exponentially with some energy, but there's a negative sign also. Now we can actually vary the temperature. We can increase the temperature to make the reaction more feasible. So that basically increases the chances of crossing the reactant to the product side. However, we can also reduce the barrier out by itself by modulating the EA, or the activation energy, and that we can do by catalysis, where it means that it is not actually crossing the old barrier that goes to the product, but it finds a new barrier in a catalyzed pathway that actually takes it to an alternate route to the product. So that is the interesting concept actually in catalysis. Now we'll not consider more on these pathways, because that involves a lot of understanding on how these reactions of the molecules actually jump over a surface which is known as the potential energy surface. We'll not discuss that, but rather we'll discuss something else. We'll first discuss, to begin with, how this reaction happened, or just take an example of something which we had already discussed. Say I have a competing first order reaction, but now I'm making it a reversible competing first order reaction. So I had rate constants earlier as K1 and K2. Now I'm imposing there also K-1 and K-2. So what it means that at equilibrium, when the equilibrium is reached, I know that there is an equilibrium between A and B. So I can write it as equilibrium AB. So that is nothing but B by A, of course at their equilibrium concentration. There is also another equilibrium between A and C, which means that it will be like C equilibrium by B equilibrium, which means if we combine these two things, there is also an equilibrium established between B and C, which can be given by the ratio of the equilibrium constants, which is AB divided by AC equilibrium. Now, how will you describe it? So let us now go back again and think that, okay, fine, these two steps doesn't exist, the reverse steps. Just think that this is only irreversible transformation from A to B. And then what will happen is that suppose the reactant is lying somewhere here. This is the energy diagram again versus the reaction coordinate. We call it as a reaction coordinate, or this coordinate we call as a reaction coordinate. So by reaction coordinate we mean that it discusses the progress of the reaction along some coordinate. But of course it's not very easy to define that coordinate, but let's not discuss go into the details of what is a particular reaction coordinate. And here suppose this reactant, which is A in this case, goes to the product either B, or goes to the product which is I think we the last class we took an example of C here. Okay, and then let us also assume that from A to B it goes like this, and for say A to C it goes like that, and A to B it is going like that. Now think about it. We said that if K2 is greater than K1 for that irreversible path, so we showed that that the time traces like A will fall, and then B and C will rise, but then the C will be higher than B. The reason being the K2 is much larger than K1. Now what is K2 and K1? In Arrhenius picture, K2 is nothing but the associated it is related to the associated activation energy for this path, and K1 was nothing but the associated activation energy for this path. So this is related to so it is the activation energy for path 1, just K1, and this is activation energy for path 2. Now you see that since the activation energies are smaller for path 2, which means K will be larger because it goes as e to the power minus activation energy. So this reactant can easily cross this barrier because the height of the barrier is smaller than it crosses this. So at a very early time, if the reaction is totally controlled by kinetics, so you will see that the C will always dominate B. And if it is irreversible, then of course A will go to 0. Now suppose we are imposing the reversibility situation. So then what will happen? So in a very long time, A will of course fall, but A will not go to 0 because A will go to its eventually go to its equilibrium concentration. So this is nothing but this concentration is nothing but A equilibrium. And similarly B and C will rise. Initially you might have a situation that C is rising above B. The reason is C has from going for A to C you need a smaller activation energy, so the rate will be faster. However, if you wait enough and allow the reverse reaction also to happen. Now what is the reverse reaction? Reverse reaction activation energy is this. So this is the activation energy for -2. And if you allow that to happen, so then you see that for the reverse reaction of this, actually it can easily come back here, and then it can go to the B channel. But for the B to A reverse reaction, the activation energy is very, very high. So it is -1. So once it goes into the B, it cannot come back. So what will happen initially, you might have an increase in the reaction, increase in the amount of C. So if you follow the C by B ratio, it will increase. But then as it reaches the equilibrium, it may so happen that it actually falls. And initially you might see the B actually goes like this, but eventually it just takes over. So if you follow at this part, or say below this part, which is the vertical line, if I, this is the time profile, so I see that the C is always above B, because I started with A, there was no B or C at the beginning. So then as it is forming, I see that of course C is forming at a higher rate because the activation barrier is smaller, and B activation barrier going from A to B barrier is higher. So it is forming. Now as C and B are forming more and more, now they can also go back because there is a reversibility imposed in the reaction. Now C can go back to A very easily, and A can also go to B, but B to A back reaction is not so favorable because the activation barrier is very large. You can also think about this in terms of the equilibrium constant. The way I have written it, I have posed the B much below than C, which means thermodynamically B is more stable than C, and all this ratio B by C will be now controlled in the long time limit or in the thermodynamic limit by the equilibrium constant. Now if AB equilibrium constant is higher than AC equilibrium constant, then which means actually it is nothing but the ratio of B equilibrium by C equilibrium, we'll see that B will have a more population, the amount of B will be more at equilibrium than C. So initially I might have that C is forming at a faster rate than B, and I'll see actually the C is higher than B. But eventually as the time progresses, or if we allow enough temperature, if we increase the temperature, then these back reactions also happen. Then the overall population will be dictated how stable is the product, how it is. If it is more stable or less stable, that stability will control the total amount of the reaction, which will be controlled solely by the reaction free energy for the individual paths, and the ratio will be controlled by their individual equilibrium constant ratios of the equilibrium constant. So this is a very interesting concept, and in this case we call this C as kinetically controlled product, because if you do it at low temperature or at a very short time, then you will see that C is forming more, because the kinetics of forming C is very fast, because that is followed as because K2 is much larger than K1. Initially it is working as if it is irreversible because there is no B and C to begin with, so there is no question of reversibility at a very early time. Now as time progresses, so it is kinetically controlled product. Sometimes we call it as a KCP. And B, as time progresses, or if you allow enough temperature to the system, then this reverse reaction also happens. But then everything is controlled by the equilibrium constant. And also you can think in the other way that since B is actually energetically at the minimum position, the reverse reaction for B to A will be much slower because the activation barrier is also very high. So it will be very much not only kinetically not only thermodynamically favored, it will be also kinetically inert. So thermodynamically controlled products are also kinetically inert in the sense the back reaction is slow. So B is called as thermodynamically controlled product. So in the long time or in the high temperature limit, you will see that B is forming more than C. So you'll see the C curve is down here and B curve is here and A is here. So this is where basically everything has reached the equilibrium at a very long time, or you could achieve it in a very quicker time by increasing the temperature, by allowing all the reverse reactions to happen. And then you can look at the rates and you can easily figure out that B to A back conversion is very difficult. Here what we also see that if two reactions are in equilibrium via a common species, the common species is A here, the B and C are also in equilibrium in principle, because we showed that B equilibrium by C equilibrium is a constant, and that means it is going via A, of course, because there is no direct interconversion of between B and C. But this example shows how the very simple concept which was put forward by Arrhenius in terms of the activation energy can tell the relative ratios of the product at a very early time, where actually kinetics controls governs everything, and at a later time their the thermodynamics controls everything. Now, you should not have this notion that the products which are kinetically controlled should not be thermodynamically controlled. It can be both ways, meaning I could have drawn this thing in a very other different way. Like I could have drawn this, suppose this is the reactant, and then I could have drawn the B here with a smaller barrier, and then C here, which is thermodynamically less stable, with a larger barrier also. So here actually the barrier from going to A to C is higher. So here B is both thermodynamically controlled as well as kinetically controlled. So that actually depends. So the way I have drawn here in the first picture, I showed that distinguishing feature, what will be the if one product is kinetically controlled and the other product is thermodynamically controlled. But it may be the situation that the reaction favors a particular product, both thermodynamically as well as kinetically. So from the very beginning, you will see that it's only B that dominates, and it will keep on dominating as the equilibrium is reached when in the long time limit. So this depends on the relative energies and activation barrier of these individual paths. Now the next thing that we are going to study is basically catalysis. Now already we discussed that what is a catalysis and what is a catalysis. Now a catalyst is a substance that doesn't take part in the reaction, but it is you know that it is basically regenerated during the after the reaction is over, but it takes part actively as a constituent in the reaction. And the particular way catalysis or the range of catalysis, or the particularly the examples we are going to give are called homogeneous catalysis, in the sense that the catalyst is in same phase as the reactant. So like for example, you are using a liquid solution where the this catalyst is in liquid phase, as well as your reactants and products and everything are in liquid phase. So that is known as homogeneous catalysis. Now a catalyst by definition, as we just said, that it doesn't take part in the reaction. It takes part in the reaction, but it is not totally consumed. There is no net consumption of the catalyst. Let us give you an example. All of you know this thing, like say I take an ester, so ester of say like this, where R and R prime are just some alkyl group, and so this is an ester bond, COO, and then we considered first the acid catalysis hydrolysis. So if in water, say for example, now in water what we'll have is you have if you add acid in water, the active form is nothing but this, so hydroxynium ion. So then what you can have, that this proton can be captured, and you can have a situation like this. We'll have R, C double bond O, O, H, R prime with a positive sign. It's now what you can have in the second step, you can have actually in a medium the water is also present, and then the water lone pair oxygen, here basically the lone pair of the oxygen attacks, can actually attack this carbonyl center, and then after opening and reopening in organic chemistry language, it can give you the product like R, C, O, OH, you can easily see that. Okay. And then you have R, O, H. So and then of course this proton also leaves, and it can be taken up by another water molecule, and you can have this proton can be taken up, and you can have actually H3O plus again regenerated. So that's the catalyst here, which actually started the reaction. But in the net reaction, as you can see, one molecule of water got just consumed. That is the overall thing in this reaction. So it's just addition of one water molecule. However, we see that it is catalyzed by hydroxynium. Actually, it is catalyzed by proton, but the active species is H3O plus, because H plus never exists in H2O. Water acts as a base and then forms a conjugate acid, which is H3O plus. Similarly, you could also think about this reaction being proceeded via and base catalysis, where I have instead of H3O plus, OH minus, and OH minus directly attacks the center, and you can have situation like R, C, O, OH, and then you have basically R, O minus, and then you can have a further addition of water, in the sense that a proton can be abstracted from water, because this is a very strong base, and then you'll have R, OH plus OH minus, and then you can see this OH minus is regenerated. So I'll have RCOOH, and in an effect, actually this water is consumed. So that is also another example of to write it as here. This is plus OH minus. So this OH minus is regenerated, and you can see that we have just given you an example of acid catalyzed hydrolysis of the ester, as well as the base catalyzed hydrolysis of the ester. So these are two different pathways, by the way. So the base catalysis, if I remember correctly, is actually a slower process than the acid catalysis reaction. So if you do this experiment, you take something like, say, ethyl acetate, and then you put some acid, heat it, warm it up, and you will see that this acetic acid is generated in the mixture, and that acid you can titrate against some known volume of alkali and try to figure out how much acid is being produced in the reaction, and then you can actually find the rate constant also of the hydrolysis of this reaction, and then you will figure out that just adding water, it doesn't hydrolyze. Maybe at warming up it may hydrolyze, but just by adding acid, the rate actually increases by whole a lot. And for base catalysis, it is a little bit slower than acid catalysis. So you need also to elevate the temperature. And one more interesting thing for this particular example, since I gave this example, is that when you have the ester and you have the water, basically hydrolysis is nothing but addition of water, and then you get some acid plus alcohol back from the ester. Then the question is, the water, this reaction, it's kind of an elementary reaction, because in the rate determining step, the water actually attacks, and that step controls the entire step of the entire course of the rate of the entire course of the reaction. And then you can always suggest that this water molecule or this actual addition of water, or the attack of the water on this ester, since this is the rate determining step, the rate will be more or less proportional to the concentration of these two, but so it will be something like this into ester, the observed rate law, However, water is present in very large excess, because when you do this experiment, you put a lot of water here. So the concentration of water doesn't change much, which means this concentration of water is almost constant, and then you say that, okay, it is a bimolecular reaction actually, but it appears that as if it's a not bimolecular, sorry, it's a it is actually a second order reaction, but it looks like that it is a first order reaction, which actually only depends on the concentration of the ester. And the observed rate law is actually known as, it's a first order rate law, but it is not exactly first order because it's a second order. So these kind of reactions we call as pseudo first order reaction. Pseudo first order reaction. So it is not actually first order, but we made a condition in such a way that one of the component is in large excess, so that concentration does not change. So then the then the second order reaction actually behaves as a first order reaction. Now in the next lecture, under this lecture, in the next topic, we'll discuss about enzyme kinetics.